All right, good morning, everybody. Couple quick announcements. So this week we have our Sunday mini quiz and homework. We didn't have one yesterday because Tuesday was a Monday. And then next week we will finish up chapter 2, and then our chapter 2 quiz will be next week on Friday. So just keep that in mind. It's going to be similar in structure to the chapter 1 quiz. There'll be 10 questions, multiple choice. You'll need to do it in a 1-hour period. There will be reviews for the chapter 2 quiz next week on Monday and Thursday. And I will send out an email on Sunday with a summary and the links for those. So we'll talk about that a little bit more next week, but I just wanted to put that on your radar just so that you don't let that slip by. So today we are just sort of continuing in our chapter 2 work, and today we're going to be considering units of the derivative as well as thinking about applications and how we will use the derivative. Well, you guys are a little bit frozen. I'm going to wait a second. Hopefully you unfreeze. Okay, still frozen. Okay, if you're live streaming in, we're just going to wait a minute for them to log back in. if you're on the live stream, I'm just waiting to get an update from the grad TA. I'm guessing there's some sort of technical malfunction in Marcus. So as soon as I have an update from him, I will let you know, and hopefully we'll be able to start in the next couple minutes. Sounds like for now they're having some connection issues, that the internet's not working. I'm not sure if it's an Eduroam issue or a Marcus issue, but he's going to keep trying. So hopefully we can start in about 5 minutes. But if you don't want to wait, you can certainly watch the asynchronous video right now instead of the live stream if you would like to use your time now and not have to wait. But you are also welcome to wait, and hopefully we'll be able to reconnect in the next 5 minutes.
Professor.
All right, can you hear me okay?
Yes.
All right, and we're back. All right, sorry about that, everybody. Hopefully that will not happen again, but let's get rolling. So we're in chapter 2. Today we're going to be talking about interpretations of the derivative. So what that really means is we're going to be really honing in on units, as well as one application in terms of prediction. So I'm going to go ahead and switch over to the doc cam. Okay. And so as a reminder, when we talk about notation and things like that and units and all of this, there's 2 types of notation that are going to come up for us. And again, that is because calculus was developed by 2 separate people at the same time who had their own unique notation, and both sets of notations still are with us today. So we see f prime of x, which is Newton's notation for derivatives or instantaneous rate of change. And then we also see stuff like dy dx, which is the Leibniz notation. And so these are sort of generic. So for example, if your function has a t in it, then you would see f prime of t, right? And then this would be dy dt. So these letters are going to change based on the function you have, but these are sort of the general way that we're going to notate it. And oftentimes you'll see when people talk about the derivative with dy dx, they talk about it in terms of looking at the difference in y values over the difference in x values, which may look familiar to you because that's how we talk about slope, right? And remember, the derivative is the slope of the tangent line. So when we talk about the units of the derivative, it's a little bit easier to see it in the Leibniz notation because we're going to be doing the units of the dependent variable, which is typically y, but of course can be any letter that we want, divided by the units of the independent variable. Okay, so it's a ratio. And so the dependent units, y over the x unit. So it's the same setup as the way we set up the derivative. So it's the units of y over the units of x. Okay, so today we're going to be thinking about when do we actually apply this and how else do we need to think about what we've been doing in terms of interpretation and how we sort of put all these things together. So suppose that the position of a falling stone is given by s of t in meters and time t is given in seconds. Then f prime of 4 equals -7. What does that mean, right? This is what we're trying to get at. So how do we know where sort of the derivative units go versus other types of units? And so when we think about this, we really need to think back into how we've sort of set up derivatives. So here, our independent variable is time t, which is given in seconds. So our independent variable in this situation is time, and the units are seconds. And we see that time is what's being plugged into the position function. Now, the dependent units here are going to be the position in meters. Okay. So the dependent units go with the dependent variable, which is meters. So we have the independent and dependent variables separated within the word problem. So how do we then apply it to a statement like f prime of 4 equals -7? So one of the key things that's really important is that whatever is plugged into a function or the derivative or even the second derivative, which we'll get to at some point, this is always the independent variable. Okay, so just like we have f prime of x, x is the independent variable in this generic form, this 4 is directly tied to the independent variable because it's answering the question, where are we looking at what moment in time? So the 4 here is going to have units of seconds. So the number that's plugged in does not have the derivative units. Okay, it has the independent value units because that is the value we are choosing to evaluate at. The derivative is what is being calculated and comes out on the other side. So it's the -7 that is the derivative, that is the rate of change. The -7 is the instantaneous rate of change. So it's the -7 that gets this ratio. So the units here of -7, and slide them over here, are going to be the units of the dependent variable, which is going to be meters, divided by the units of the independent variable, seconds. Okay, so here at time equals 4 seconds, right? 4 seconds, this is the moment in time, the rate at which the stone is falling is -7 meters per second. Okay, so again, the derivative units go with the output from the derivative, and the independent units go with the input of the derivative. Okay, so it's important to be able to know when we're using the derivative units and when we're not. So that's something we're going to be practicing a lot today. Okay, so we're going to skip down to example 1. This just has some notes on how another way you can think about small changes. It'll make more sense if you go back and read these after we do what's called the tangent line approximation. But since we're a little short on time, I want to make sure we do lots of problems today. So example 1, if S of t is the position of a moving object in feet and time t is measured in seconds, find the units of the derivative of S of t, which is also known as the velocity. So this is similar to the one we just did, but we're not evaluating at a point. We're just asking what the units of the derivative are going to be. So for part A, you're looking for the units, again, by looking at the ratio of the dependent units over the independent units. And then we're also calling that velocity. So that derivative is named velocity. And that's important because in part B, we're saying, well, what if we have velocity and it has the same units as found in part A? So we're taking that velocity function and making that now the dependent function and asking, what if we take the derivative of that? Then what are the units? So part A is what we had done in the last example. Part B is taking it a step further to see if you can figure out how to apply a second level of doing this. So I want you to try this out. Take 2 minutes, see what you can come up with in terms of the units. If you're not sure, do your best guess, and then we will go through it together. Okay, take about 30 more seconds. All right. So whenever we're trying to think about units, I always encourage you to underline them and really think about what is the dependent and independent variables that are attached to these units before you start to answer questions. I think that that's pretty helpful, but it's really up to you. So here we have S of t in feet. S of t, capital S of t, is the position, and that is our dependent variable, which means our dependent units are going to be in feet, okay? And then for our independent variable, we have time t, which is measured in seconds, okay? I know that t is my independent variable because it's S of t, and so the thing that we get to pick and plug in is t, and so time here in seconds. So what we're asked to do in part A is to find the units of the derivative of position. So since we have the dependent variable and the independent variable identified, we can look at the ratio. And so we have feet on top from the dependent variable and seconds on the bottom from the independent variable. So the rate of change of position is feet per second. The units will be feet per second. And within this, we are also told that when we take the derivative, that this is known as velocity, which means that velocity has units of feet per second, right, as a dependent variable. And that's going to be important for part B, okay? So part B says if the velocity of an object has the units found in part A. So what does that mean? That means that velocity is now my dependent variable, and velocity has the units of feet per second. Then what are the units of acceleration, which is the derivative of velocity? So we have the units of the dependent variable, feet per second. We also have the units of the independent variable because the independent variable does not change as you take derivatives. Okay, the independent variable is always the same, whether you're taking the first derivative, the second derivative, the 10th derivative. We've only really been talking about first derivatives, so this is sort of our foreshadowing into a second derivative. So here, what we are trying to figure out are what are the units of v prime of t, the derivative of velocity. So that means we need to take the dependent variable units, where the dependent variable is velocity, so feet per second, and then over the independent variable units, which again didn't change, right? Because it's the same function. We're always plugging in that same t. So per second. And so we can simplify this. If you have feet per second and you divide by seconds, you get feet per second squared. Okay. And now, just like in part A, we have a special name for the derivative of velocity. And the derivative of velocity, we are told, is acceleration. Okay. So thinking about this sort of in the big, broader context, right? We have position, which is s of t. And that could be something like 10 feet off the ground, 30 feet off the ground. Like, how far is this stone from the ground, right? When we take the derivative, we get velocity. And velocity answers the question, how quickly is that stone moving, right? 3 feet per second, 10 feet per second, 20 feet per second. Like, how quickly is the position changing over time? That's the first derivative. Here, when we take the derivative of velocity, we're asking, is the rate at which the stone is falling speeding up or slowing down, right? So we know with things like gravity, if something is dropped, it's going to speed up. But then what if it hits the water? It's still going to fall, but now it's going to slow down. So it's asking how the rate is changing. And so since the derivative of position is velocity, that means if we take the derivative of velocity, that is actually the second derivative of position. So the first derivative gives us this, and then we took another derivative to get acceleration. We're going to be talking about second derivatives on Tuesday. So this is just sort of, like I said, sort of a foreshadowing in why we might want second derivatives, because they do give us information about rates of change. Today, we're focused on units. So this is how we have to take this information to then put this together to talk about units of acceleration. Okay, so let's look at another example. Oops. I'm gonna trace this picture for a second because I think it's a little bit light. I have a function that looks like this. And what do we want to do with this, right? So 8, 16, 24, 32, and 40. This is kilograms, 3, 2, 1. Okay, so here we have this graph, and what this graph is telling us is the size of a baby in kilograms based on its age and weeks. Okay, and so this is in gestation, so while the mom is growing the baby. So we want to approximate how the baby's weight is changing, the rate at which it's changing at 20, so g prime of 20. So we've talked about thinking about the derivative as the slope of the tangent line. So what we want to do here is we want to envision what the tangent line is going to look like at time equals 20. And then first, we want to ask ourselves, is the slope of that line positive, negative, or 0? So if it's upward slopes, it's going to be positive. If it's downward slope, it's going to be negative. If it's horizontal, it's going to be 0. And then we're going to take it a step further today. So today what we're going to do is we're going to try to picture what that tangent line is going to look like and try to approximate 2 points on that line. So once we've sort of pictured where we think that tangent line is going to go, what are 2 points that it goes through? Because if we have 2 points on the line, we can then get the slope of the line. So we're going to approximate the slope of this tangent line to approximate the derivative. And once you have a value for your approximation, then we're going to bring in the units. So again, here you see that this is giving weight in kilograms, and this is giving weeks in terms of age. So we need to think about those 2 different units and how they would apply to the derivative. Okay, so I want you to take 2 minutes, see what you can come up with, try to approximate it, try your best. It doesn't have to be perfect, but definitely really think about what the units of your approximation are going to be. Okay, try it out and then we'll go through it together. Okay, take about 30 more seconds. Okay. So again, we want to envision the tangent line, and then we want to pick 2 points that we see on that line. Now, you may not pick the same 2 points I did, and that's okay. You can pick any 2 points on the line, depending on what you think will be most convenient. But your approximation should be in the same general range as what I get. So I use the point 40, 1.5, and then the point 16, 0. Okay, you could also use the point 32, 1, 24, comma half, right? Anywhere sort of on this line. And your line might be a little more steep or a little less steep than mine, depending on how you sketched it in. But again, your general output should be in the same general range as what I get. Okay, so now when we are going to approximate the actual derivative, the value, we're trying to find the slope of this line. So we're going to do change in y over change in x. So we have 1.5 minus 0 over 40 minus 16. I'm expecting my output to be positive because I see that this is positively sloped in the upward direction. And I can see from the numbers here that I will get a positive number. And so when I plug that into my calculator, I get 0.0625. So again, if your line was a little bit steeper or less steep, you may not get this exact number, but you should get something like, between like 0.04 and 0.08. You shouldn't be getting like 25, right? That would be very, very different. So in order to understand what this number is telling us, this is where we have to bring in the units, right? So we're really thinking about what are the units that go with this so that we can then talk about what this number means. So again, we want to identify the dependent variable units and the independent variable units. Here, we're going to get those directly from the graph. So the dependent variable and units will show up on the vertical axis, and the independent units and independent variable will show up on the horizontal axis. So here, for my dependent variable, I have kilograms, and for my independent variable, I have weeks. So here, I have kilograms per week. Okay, so those are the units. So what does this mean? What does this tell us? So what this says is that when the baby is 20 weeks old, 20 weeks in gestation, that it is increasing or growing, because it's positive, by 0.0625 kilograms per week. So at that moment in time, we can expect that 1 week later, it will have grown by 0.0625 kilograms. So for every 1 week, this is how much it's going to increase. And again, I know it's increasing because it's positive. So this unit helps us put this number into context. Okay. So we're going to practice another unit, and this one's a little bit tricky. So I don't want to give too much away, but I'm just going to read it to you, and then we're going to do 2 statement interpretations here. Okay. The first one is just for a regular function, f of 100 equals 7. The second one is the derivative function, f prime of 50 equals 4. So this one does not have a derivative, and this one does, so keep that in mind. So here it says, the time for a chemical reaction, capital T in minutes, is a function of the amount of catalyst present, A, in milliliters. So T equals F of A. So you're asked to interpret these 2 statements with these numbers using these variables and units. Okay, so I want you to take 2 minutes, see if you can come up with statements. Again, you're really trying to match numbers to units. So just be really careful about that in your units. And then in 2 minutes, we'll go through it together. Okay, take about 30 more seconds. So again, I want to start by just looking at the setup and determining what is my dependent variable and what is my independent variable. So here, looking at this final statement, I see that T is going to be my dependent variable. And so T is in minutes. So this is my dependent variable. And it's talking about, this is going to come up with our sentence, the chemical reaction, right? So how long does the reaction take? And then my independent variable here, I can see is A, is what I get to plug in. And A is in milliliters. And what is in milliliters? The amount of catalyst. So my units here are minutes and milliliters, and I need to put that all into context with these numbers in terms of both the function and the derivative. Okay, so I have my dependent and independent variables labeled here, the green independent. And now I'm going to tackle putting this all together. So f of 100 equals 7. I have to figure out what the 100 units are, what the 7 units are, and then put it together in a sentence. So as a reminder, the number that goes inside the function is your independent variable, right? So my independent input, or my value here, is 100. And so that's going to be in milliliters. So my 100 in milliliters. And then the 7 is my dependent units, and my dependent units are in minutes. So that 7 represents 7 minutes. Okay, so how do I put that together in terms of the whole big picture here, right? So when we're talking about milliliters, we're talking about milliliters of the catalyst, which is something that speeds up a reaction. And when I talk about 7 minutes, I'm talking about the reaction time, right? How long the reaction takes. So I would say something like when 100 milliliters of catalyst are present or used, or however you want to say that, the reaction takes 7 minutes. Okay, so the relationship is between the 100 milliliters of catalyst and a reaction time of 7 minutes, right? So this is just one way we can write a sentence. It doesn't have to be exactly like this. You could say, you know, the chemical reaction time is 7 minutes when there's 100 milliliters of catalyst, right? So like the order isn't what's important. What's important is that we're grouping the 100 milliliters of catalyst and the 7 minute reaction, right? And then you can put it into a sentence however, you know, you see fit. So this one is really interesting and sort of what I was alluding at, because time here is not the independent variable. Time is commonly used as an independent variable, but it doesn't have to be. So that's why we need to be a little careful here, because our brains definitely like to default to what it's used to. So let's look at part B. So we have f prime of 50 equals 4. So as I mentioned before, whether you take a derivative or you have an original function or you have a second derivative, whatever is being plugged in is always the independent variable. Okay, so that's not going to change from A to B. So this is still the independent variable that we're plugging in. And so again, this is going to be 50 milliliters. Okay, because we're asking at what moment in time. Well, our moments in time here are measured by the amount of milliliters. So when we have 50 milliliters, what's happening, right? So it's the 4 that the units are going to change. So the 4 is going to have the derivative units, the rate of change units. And this is where we need to go ahead and do our ratio of our dependent variable over our independent variable. So the 4 is 4 minutes per milliliter. Okay, and this is where your brain might automatically try to switch them, because minutes is almost always in the bottom, but here it's not, because we're talking about how the amount of time changes based on the amount of catalyst. So it's a little weird. So, you know, if it tripped you up a little bit, that's pretty normal. Your brain's trying to be consistent with what it usually does. So how do we put this together? So we're talking about what happens when there's 50 milliliters. So when 50 milliliters of catalyst are present. Okay, or are used. You can say present or used, but the idea is that we've added 50 milliliters of this catalyst. The reaction, so now we're talking about how the rate of change of the reaction is happening. So not the amount of time, like we did in part A, but the rate at which the reaction is changing. So I'm going to say the reaction increases by 4 minutes per milliliter. Okay, I can use increases because the 4 was positive, right? So if your rate of change is positive, then the change is increasing or growing. If it's negative, you could say it's decreasing. You could also just use the word changes if you'd prefer. But the idea is that the reaction is changing or increases by 4 minutes for every milliliter you add. So whatever the amount of time is at 50 milliliters, if we were to add another milliliter to 51, the reaction would increase by 4 minutes. So if it was 2 minutes at 50, it's going to be 6 minutes at 51. So it's telling us how the time is changing. Okay. So like I said, this one's a little tricky, but hopefully you were able to figure out some pieces of that. Let's go ahead and look at another units problem here. Okay. So the amount of medicine in milligrams found in the bloodstream, C of T, C for concentration, is a function of time T in minutes after taking the drug. So let me set up what is happening in this scenario. So let's say you have a headache and you take an Advil, okay? If you were to measure the amount of Advil in your blood after a certain amount of time, that is what is being set up here. Okay, so the concentration of the drug in milligrams in your bloodstream after some amount of time T, which is in minutes. Okay, so that's sort of the scenario here. So what we want to do for part A, we want to interpret the statement C of 35 equals 90. So thinking about what the units of 35 and 90 are. For part B, I want you to think about how we would write this particular derivative with these variables in Leibniz notation. You can also do it in Newtonian notation. The point here is really to identify how we use the variables that are in the context. And then for part C, I want you to interpret the statement C prime of 15 equals 7. So the derivative at 15 equals 7. So again, thinking about the units and how they play into these numbers. Okay, so take 2 minutes, see what you can work out for A, B, and C, and then we will go through it together. Okay, take about 30 more seconds. All right. So again, we want to make sure we identify the dependent and independent variables so that we can get the correct units. So here, our dependent variable is C of T, which represents concentration, and the units of that are in milligrams. So here, you'll see that these are sort of pretty far separated in the sentence. So we just have to make sure we are connecting them back together, okay? And then our independent variable, we see is a function of time, T in minutes. So here our independent variable is time, and the units are going to be in minutes, okay? So for part A, interpret the statement C of 35 equals 90. So again, the number getting plugged into the function is your independent variable. So that number 35 is a time in minutes. So 35 should go with the word minutes. And then 90 is connected to the dependent variable, which we said was in milligrams. So if we were going to put that together in a brief sentence to talk about what's happening, right, we would say something like, after 35 minutes, or at time equals 35, there is 90 milligrams of the drug in the bloodstream. Okay, so we're noting the amount in milligrams that are present at a particular time. Okay, so again, your sentence doesn't have to be exactly the same as mine, but it should have something about 35 minutes and 95 or 90 milligrams of the drug. Okay, so for part B, we want to write the derivative of this function using Leibniz notation. And I said you go ahead and do it with Newton too. The idea is sort of to connect back to the letters that are being used to represent what's happening in the problem. So with Leibniz notation, we have the ratio of the dependent variable over the independent variable. So we would write this as dC dt, the derivative of concentration over time. And again, this is just for recognition. So if you see this in another context, you remember that this means the same thing, right, for derivative. And if we were going to write it with Newtonian notation, we would have C prime of T. But the idea here is that C and T are the two variables that we are using in this particular problem. Okay. And then for part C, we're interpreting the statement C prime of 15 equals 7. So as a reminder, the 15, again, independent. Anytime you have something inside the function, whether it's the function or the derivative, that is the independent variable. So that means that that 15 is going to be 15 minutes, right? So we have 15 minutes. And then it's the 7 that we now need to apply the derivative ratio, because now we're talking about the derivative. So that 7 is the rate of change. So we're going to do the ratio of the dependent units over the independent units. And so that's 7 milligrams per minute. Okay, so how do we put this all together to come up with a sentence? Okay, so we could say something like at time equals 15. And again, you could say after 15 minutes, but something about it happening at 15 minutes. The amount of drug in the bloodstream is increasing by 7 milligrams per minute. Okay, so again, we're talking about the rate of change now, which means that we're expecting at time equals 16. So 1 minute later, we will have increased by 7 milligrams. Okay, that's what that's telling us in part C. So when we talk about units, we often are going to be integrating them into problems that we're doing to help us have a context or better understanding of the answers we're getting. So you'll see that this is going to become part of the problems that we're doing, but not the whole entire problem. So oftentimes when we get through to chapter 3, we'll be calculating lots of derivatives, but then we also need to include the units from the setup to be able to talk about a solution, right? So that's sort of the big picture on units here. But as I mentioned, there's sort of another application that we're going to do today with derivatives that help us understand why they're going to be so important, right? So you're taking this class on calculus and somebody in your major, or maybe you just really liked it, decided that this was going to be important. And the most powerful aspect of calculus 1, right, of doing these rates of change, is to be able to make the best predictions we can about things we don't know. So we did this on a small scale when we talked about periodic functions. We said if there's a pattern and it repeats, we can use that to predict what will happen later because there's a pattern, right? But when there's not a pattern, what we can do is we can think about what information do we know right now about something that's happening, and what is the rate at which that thing is changing? Because if we know that, then we can use that to predict something further down the line. So for example, and this will tie into another example we do, you will often see predictions about what the world population will be in 5 years from now, right? How do you think they get that number? They take the current population of the United States or the world, whatever they're measuring, and then they look at how that has changed over the past year, the rate of change. Did the population increase? Did it decrease? By how much? And then they use that rate of change to say, if we keep going with this same rate of change, then we can predict what the population will be in 5 years, right? We use this in weather. We look at how weather is changing and the speed and velocity at which it's changing to make predictions of what the weather will look like in a few days. We use this in all sorts of things, looking at the solar system, looking at chemical reactions, looking at, some people use this to look at stocks and bonds in the market. I don't think that's a good idea. Stocks are volatile. But the idea is that if you have information about what's happening right now and the rate of change, you can use that to try to guess what will happen at another point in time. So that's what we're going to do here. We're going to think about how do we mathematically set something up where if we have information about what's happening right now and the rate of change of whatever it is, how do we use that to think about what might happen at a different point in time? And so this process has sort of two names. We call it the tangent line approximation, and it's also called local linearity, okay? And so the sort of big picture idea, I'm going to draw you a function, is let's say we have some data about something, and let's say the data looks like this, and this is like where we are in time, right? So let's say this is 2022. This is what we know. This is what's been happening of whatever the thing is that we're measuring. So this has some value here, some number. But we also know the rate at which our function's changing because we can approximate a tangent line. Right? So we have some sort of rate of change. And so what the tangent line approximation does is it says, okay, we can predict what will happen next year, so 2023, by just taking that rate of change and applying it to the value. So we predict it's going to be here based on the rate of change. Okay, that's what's happening in the background. Now, if we are going from 2022 to 2023, that's probably a decent way to make this approximation, right? Because we're pretty close to the same year that we have information for. If we wanted to predict what was going to happen in, say, 2075, this is not a very good approximation because all of a sudden we've decided that this is going to increase forever and that, it's not going to be volatile, whatever we're measuring. And that's just really not true. So one thing you have to keep in mind when we do tangent line approximations is that the closer you are to the original information, the better your prediction. The further out you go, the less accurate it'll be, right? So you always want to make sure you have the most up-to-date information and adjust your prediction as you get new information. Okay, so what does this look like in practice? So we can find the approximation and value of a function at a point. And if we have information about a point and the derivative at that same point, we can use it to approximate a nearby point. Okay, so the general function looks like this. F of x is approximately f of a plus f prime of a times delta x. And so I want to talk about what these pieces mean. So here, f of a and f prime of a, this is the information we have. This is the point of time where we actually have accurate information that is not yet a prediction. So this is the information we have. Okay, so this would be like the point and the derivative at that point, right? We have that somehow, either through computing it from accurate data now or for whatever reason. Now, f of x, this is the point we want, right? So if we're trying to predict what's happening in 2023, x would be 2023. And a would be 2022 is what we had, right? So the point that we're trying to approximate, that's what's over here on the left, f of whatever we're trying to figure out. Now, delta x, okay, is the difference between the point that we have and the point that we want. So how far away are we predicting? Okay, and the way we do this calculation is x minus a. So the point that we want minus the point that we have. And this calculation right here helps us understand how accurate our prediction is. If this ends up being low, like 1 year, not bad. If this is a big number, that means we're predicting far away, not as good. The order is important. So sometimes we are predicting into the future, but sometimes we are predicting backwards, which means it's probably not time, but there's some reason we don't have the information before. And so it's always x minus a. Okay, so let's look at an example of how we could apply this, and then we'll do some practice problems here. So suppose that we have a particular function where g of 5 equals 10 and g prime of 5 equals 3. So what I want you to notice is that we have information about a function at a point and the derivative at that same point, where that point is 5. So at x equals 5, we have information about the function and the derivative. We want to use that to try to approximate g of 7 and g of 1. Okay, so we're going to do one of these together, and then I'm going to have you try one. So we'll do g of 1 together. So g of 1. Okay, so what we're going to do is we're going to say this is what we want, g of 1. We're going to take what we know, so g of 5 plus g prime of 5, okay? And now g prime of 5 is multiplied by delta x, which is the number we want, 1, minus the number we have, 5. So that's how many units we are approximating away. So once we have this set up, we are going to plug in all the values that we know. So g of 5, we said was 10. G prime of 5 is 3. And 1 minus 5 is negative 4. Okay. Now, this is going to sound really silly, but I need to emphasize you have to do this multiplication first, right? Order of operations. So these two numbers have to get multiplied before you add on this value. The number one reason students get problems like this wrong is because they add first and then multiply. You have to multiply first, okay, because of order of operations. So 3 times negative 4 is negative 12, plus 10 is going to give me negative 2. So my approximation for g of 1 is approximately negative 2. That is my guess for what that value should be based on the information I have, okay? So I want you to try to do this now for g of 7. Okay, same idea. We're still going to be using information from g of 5 because that's the one that we have information for. So try it out. See if you can get an approximation for g of 7. Okay, take a minute and a half. And then we'll go through that one together. Okay, take about 30 more seconds. Okay, so again, if we want to predict what's happening at g of 7, we still need to use information about g of 5 because that's what we have information about at the point and at the derivative. So we have g of 5 plus g prime of 5. And now to see how far we're moving away, we're going to do 7 minus 5 because 7 is the number we want and 5 is the number we have. So that's the distance on the horizontal axis between our 2 points, the one that we have and the one that we're approximating. So we said g of 5 is 10. We said g prime of 5 is 3. And then 7 minus 5 is 2. So again, we're going to multiply first. So 3 times 2 is 6, plus 10 is 16. So we have an approximation for g of 7. Now, one thing that I want to point out, and as a reminder, okay, I want you to think about this particular calculation right here. This has a difference of 4 units in the negative direction. This has a difference of 2 units in the positive direction. So 7 is closer to 5 than 1 is to 5. So this is a better approximation. Now, there's nothing we can do about that, right? Because for g of 1, we don't have any other information. But again, the closer you are to the information you have, the better your approximation. And I'm going to keep saying this because if you end up using this with real world data in your major or something like that, it's important to know how good your approximation is sort of in comparison to other approximations. So the closer you are to the information you have, the better your approximation is overall. Okay, so now we're going to do a word problem. Now that we know sort of the function of this process, right, the tools we have to apply this formula. But here's a word problem where I want you to really think about how we can apply what we know about mathematical notation to this word problem so that we can set up something to solve that's in the form of this local linear approximation. So it says, suppose the population of a town was recorded starting in the year 2000. In 2006, the population of a town was 125,000, and the town's population was increasing at a rate of 3,200 people per year. Use this information to approximate the size of the population in 2013. So again, we have a situation where we have information about what's happening at one point in time, and we want to use it to approximate what's happening at another point in time. So think about how you can use notation mathematically to set this up, and then how we can use this process to then make this prediction. Okay, I'm going to give you 2 minutes to think it through, see what you can come up with, and then we will go through it together. Okay, take about 30 more seconds. All right. So we need to think about how to set up the information that is given to us here in a way that we can then use the formula. So I set this up in a particular way, but you may have set it up slightly different, and that's okay. And I want to talk about the differences in a second. But I set this up as P of 6 equals 125,000 and P prime of 6 equals 3,200. So I was asking, what moment in time do I have information about the function and the derivative? And the answer to that is in 2006 is what I have information about. So you can define this as, f of 6, f prime of 6. You could do p of 2006, p prime of 2006, right? Both of those are equally representative of what's happening, but the idea is that we need to have a way to talk about a function at a point in time. So the point in time that I chose was 6, since we started measuring in 2000, but you may call it 2006. That's fine. Since we were talking about population, I used P, but you could use F, right? It means the same thing, but the idea is that we have a function at a moment in time, okay? So this is the information I have, and this is how I'm choosing to write it, but hopefully you have some way that you've written it that's some sort of equivalent way where we have something for 125,000 and the derivative of something for 3,200. So from there, I want to approximate the population in 2013. So for me, I'm looking for P of 13. If you use 2006, then here you would use 2013, right? Same setup. So I'm going to use P of 13 equals P of 6, which is 125,000. Plus P prime of 6, which is 3,200, times 13 minus 6. So there's a 7-year difference. Okay, so that's what my calculation ends up looking like. I will do the multiplication first, which is going to give me 22,400, and then I will add that to the 125,000, and that gives me a final population of 140,400. Okay, so again, we're trying to think about the type of information we have. And again, if we are using this to approximate something else, that should be sort of a flag for you that maybe we're doing tangent line approximation. So if it says approximate what's happening at this point in time, then you're like, oh, maybe this is the process where I'm doing tangent line approximation. Okay, so let's look at one other way that this can come up and think about how we can use all the tools that we have so far in the class to make this work, basically. So suppose the table below gives the total sales in millions of CDs for a music store as a function of time in years. CDs are compact discs. Hopefully you've seen those at some point in your life. So here, if we consider, this first data point, so this is saying in 2008, there were 6.25 million CDs sold. That's what this means. I realize at some point I'm going to have to change this example because CDs won't be sold anymore. That makes me sad. But anyways, here we have information up through 2012. So we want to use the table above to try to approximate the sales in 2013. So I want you to think about what we know, what information we have, what information we would need to have to actually use local linear approximation, and if we can actually get that information from the table to be able to use this process. The one thing I will mention, and I will say this again, the closer you are to the thing you want, the better your approximation. So I want you to think about that really carefully when thinking about which information to use. So I'm going to give you 2.5 minutes to see if you can sort of work out a good way to do this, and then we'll go through it together. Okay, take about 30 more seconds. All right. So we're trying to approximate the sales in 2013. And if we look at the table, we have information from 2008, 2009, 10, 11, and 12. And again, we want to be as good as we can. So 2012 is really the closest information we have to 2013. So here, if we set this up in sort of the general way that we have been for this type of work, we're looking for what's happening in 2013. The best information we have is about what's happening in 2012. So the general sort of formula we would set up for this looks like this, and then 2013 minus 2012, right? So the question is, do we have all this information, right? Do we have what we need to figure this out? So let's go sort of piece by piece. So F of 2012, well, that is information we have. That's the functional value in 2012, which we have from the table. So we have 4.25 plus, and now we definitely have 2013 minus 2012, right? That's just a calculation, that's just one. So the question is really, what about the derivative, right? So there's nothing inherently given about the derivative. However, we've learned previously how to approximate the derivative on a table. So that is something that we can do here. So when we approximate the derivative for 2012, we have to use the point to the left because we don't have one to the right. And we do the change in y over the change in x. So when we do that, that's going to give us negative 0.45, right? So 4.25 minus 4.7 divided by 1. So we do have an approximation for the derivative. So negative 0.45. And when we crunch this number, we get 3.8, and that represents million CDs. Now, there's one small caveat here. This is the best we can do with the information we have, right? But this whole thing is an approximation, right? We already said that we're using it to figure out our guess for what's happening at another point in time. But this negative 0.45 is also an approximation. Okay, so we already talked about how the bigger approximation, the closer you are, the better it is, but it's still a guess. Since we are also approximating the derivative, that also makes this slightly less reliable. Does that mean we shouldn't do it? No, we don't have a better thing to do. But we just sort of note that as we do any predictions, that it's an approximation within an approximation, which makes it a little less reliable than if we happen to actually know the derivative, more accurately. Okay, so have a nice weekend. I will see you guys on Tuesday, and we'll be picking up with some graphing and talking about second derivatives and some business applications.